one of the very bright minds in quantum machine learning. So we'll be discussing quantum machine learning and quantum data science today. I hope it can be as much as possible an interactive session. I'm sure that all of you guys have maybe some link with data science or quantum or machine learning. Maybe you have heard about quantum technology, quantum computing, maybe even quantum machine learning. So I hope that there is some overlap to what you guys are familiar with, and that we can skip all the marketing talk and really go into the exciting details and the what this really means for us. So let's dive right into it. So I have with me Joseph here. We're just going to have a bit of a interactive session. So maybe start here. How did you join? What do you do in quantum machining? What is your role within Cambridge Consultants, Joe?
Yeah, so I'm a quantum algorithm developer for Cambridge Consultants. So basically, I kind of fit into 3 different roles. So I do kind of research work, so looking at what the current state of the art in quantum computing is. I'd also do some kind of exploratory work on projects. For example, I've done some quantum natural language processing stuff, but I've also looked in general at quantum machine learning processes. And then I do a lot of talking, basically, about quantum computing. Which is obviously what I'm doing now.
And why the talking? Why is that important?
So I think quantum in general isn't well understood. I think there's, we hear a lot about the hype problem with quantum computing. And I think it's just clear to be, we need to be clear, honest, and open about the state of quantum computing and what it can do, and a lot of the time, more importantly, what it can't do.
So you mentioned some previous work on quantum natural language processing.
Yeah.
We'll discuss a bit more about quantum computer vision, or QCNNs, quantum convolutional neural nets, as well today. Is there any particular quantum machine learning thing that you're most excited about? What is the the primary quantum machine learning model?
So I think that the primary thing that people talk a lot about, and we'll probably touch on later, is variational quantum circuits. So which seem to be now the kind of replacement, if you like, for neural nets. So quantum neural nets are the kind of equivalent. I'm quite excited about them. I'm cautiously optimistic. There's a lot of, since it's a very new field, there's a lot of kind of traps that we can fall into easily. And I think there's some really interesting things being published currently about how we might avoid some of these pitfalls. And yeah, I'm just quite interested and excited for those.
Cool. So we'll touch a bit more on that later. So variational quantum circuits, what Joe mentioned, is kind of the way physicists like to call the neural nets. And there's quite a rich variety in nomenclature between the different fields. So buckle up, because it will be an interesting session. So let's start with a bit, what is quantum machine learning? I think there's a lot of different perspectives around this. It's not just there's not just one form. There can be machine learning that works on classical data. It can be machine learning or quantum enhanced machine learning, quantum machine learning that simulates quantum systems. What is this separation here? How do you characterize the different types, and what does this mean?
Yeah, so I think it's a very interesting topic, because it's really 3 separate fields in some sense. It's where can you put quantum into the picture? So people like to talk about characterizing quantum systems. So for instance, kind of finding the ground state energy of some chemical molecule could be a place where we have some quantum system or quantum state. And what we're doing is really classical machine learning over that state. And so that kind of sits into this kind of bottom left portion of the square that you can see there. What's also kind of widely talked about as quantum machine learning is generally just taking some classical data. So I don't know, so for natural language processing, taking some sentences and inputting them somehow into a quantum state and using a quantum computer to process that. And that's kind of the classical data quantum algorithms on the right. And then finally, we have this quantum to quantum idea of maybe we start with some quantum data. Maybe it's, we have a sensor that is inherently quantum and is outputting some quantum state. And then we're able to process this using quantum machine learning techniques. Now, today we're going to be talking primarily about this classical to quantum. So classical data, quantum algorithms.
Right. So we'll mostly talk about the top right part of this table here. Maybe some examples. What I think maybe some of you guys probably hopefully heard in the news as well is for example, the AlphaFold, right, which was a purely classical simulator that simulated quantum systems, which I think would fall on the top left bottom right approach. Maybe a quantum machine learning for correcting errors on qubit systems could be one of those as well. So really there is a whole variety of progress in all of these fields. But indeed, we will be talking mostly about the top right. I think actually the bottom right is an extremely interesting work for us as well, because there are very few players in this space that both have a quantum sensing and a quantum computing effort. And Capgemini, of course, is one of those players that does both do quantum sensing and quantum computing. Anything we want to say about this one? Why could this particularly be interesting to do quantum algorithms on quantum data?
So quantum data is kind of naturally suited for quantum algorithms in some sense. So because the data itself is so kind of high dimensional, and you're already, if your output is already quantum, it kind of makes sense to make the most of what you can do with a quantum computer. And being able to characterize kind of what that state is it will be a difficult task for classical computers. So if you can push as much of that processing onto the quantum computer, then it's a naturally quantum problem.
So we'll touch a bit later, deeper later, on what are the different elements of a quantum machine learning algorithms, and what are some of the challenges there, and maybe we can come back a little bit on why this approach would also make sense. But first, let's really dive into the top right approach. So I think one of the key challenges for quantum machine learning is that, well, we're still in the very early stages of development of quantum computers, right? These systems that we have today, they're rather small, they're extremely noisy, they can only have, they only have up to a few hundred qubits. But the number of qubits not even the biggest problem, I guess. The biggest problem is that you can only run a few hundred gates, and after a few hundred gates, the whole system break down, basically. And another general problem for machine learning, I guess, is that it's really difficult to prove any speed up. It's almost impossible to say, from a theoretical perspective, what machine learning is best. The industry standard is basically just to try it out and to see whatever is the best approach, and then move from there. For quantum machine learning, both seem kind of difficult, right? On the one hand, it's impossible to prove an advantage, and on the other hand, it's impossible to run large-scale problems. What do you think about that problem? Is that some problem we can overcome?
Yeah, I think it's a really interesting problem, because obviously, so if we look at deep neural networks, which are mostly used, in classical machine learning at the moment, they're used quite a lot. Is that we've known about them for a long time, but we've only just in the last kind of 10, 15 years been able to use them at such massive scales. And at these massive scales, our techniques for analyzing them just don't exist and don't really work. And that's kind of fine, because we're interested, if you're interested in solving problems and finding the solutions to problems, then they can do these, and you can talk about how well they perform on certain problems. But if you look at quantum computing, on the other hand, which is, I guess, slightly older than classical computing, is that we've had it for a while, and we're quite familiar with how some of the theory works, but we're not able to put this into practice. So most of our resources are spent on doing these kind of theoretical improvements that we hope will scale in some sense to the bigger data sets when our quantum computers are big enough to be able to handle them. And it's this kind of this gap in the middle that we're still waiting for, is the interesting part to me, where we can try and hopefully demonstrate some sort of potential but not leaning too hard on the theoretical grounding too much. I think there's often a kind of preference in quantum computing to be able to say we have an explicit advantage and here's the theory for it. And in a few cases where we've seen this, it's been, for example, I take some problem that I know is hard on a classical computer. So this tends to look like cryptography, for example. So if you've heard of Shor's algorithm that can be used to break RSA, and a similar algorithm can be used to solve the discrete log problem, which we know to be hard. And that's the basis for kind of Diffie-Hellman type cryptography. So if you take this hardness of a problem and invert it, you can create data sets that you can theoretically solve a classification problem on for quantum computers, and you know that will guarantee you some advantage, but that doesn't necessarily represent natural data sets. So what we have is a lot of talk about quantum advantage on things that might not be actually natural. And I think the interesting part will be focusing on things, real data sets, where we can actually kind of see some sort of advantage.
Yeah. So let's start with that theoretical basis that may give us some indication about what how quantum machine learning will work. So we thought about what are the key elements to compare machine learning models and how they are different, and we came up with these expressibility, trainability, and generalizability. And I guess none of these words are very exclusive to quantum machine learning, and they can just as well be applied to classical machine learning. But I think they are really instrumental in quantum machine learning. But they may not be very known to everyone. So maybe can we just go through them? What is expressibility in your view?
Yeah, so in my view, so expressibility, or roughly the set of functions that we can compute, if I give you some model, is just saying, how complicated really is my model. So for example, if you take the graph on the right there, you can see that I have a set of points, and that my polynomial is more expressive than my straight line. So there's an idea that because quantum computers have these kind of exponentially large spaces, that you can get some high expressibility out from them. So that's our expressibility type thing. We also have trainability, which I think is fairly straightforward. We're looking at measures here like the number of epochs that it takes for us to converge to a solution, or the wall clock time that it takes for us to complete the training cycle, for example. And then perhaps the most natural one, generalizability. And what we tend to look for in industry problems is how well does the machine perform on our unseen data, on our test set? What kind of metrics can we get out from that? So we're looking at things, standard things like accuracy, F1 score, precision recall. I think it's kind of key to say here that we're looking at measures that matter to all models. We want to be able to compare classical models with quantum models and quantum models with hybrid models. And I think this framework nicely fits all of them in.
So, and would you say that, we try to optimize all of them? Is it always better to have as much as possible trainability and expressibility, or is there some trade-off between them?
Yeah, so there will always be a trade-off. So if we think of something that is highly expressible and can model vastly complex functions, it's possible, for example, that you could overfit your training data and create something that just gets 100% right on your training set, but when you look at your test set, it's completely rubbish. So you might have massive expressibility, but your generalizability is very poor. So it's a lot of give and take, and trying to work out what exactly you want for each metric is a fine balance.
So I think that's one of the key messages that we wanted to get across also with this talk, is that there is some theoretical basis for all of these concepts, and there is a whole theoretical foundation for both classical machine learning as well as for quantum machine learning, and how we can compare these models and look for a separation where quantum machine learning may be able to do a particular task in some way better. But at the same time, there's not a golden or a silver bullet, right? Or it will be a trade-off between the different parameters, and we have to just eventually just see whatever works. But of course, it's the challenge to have as much as possible an educated guess, and to look in the right direction, and not just do this blindly. So one point that I wanted to touch on before we go to the next slide on why quantum machine learning actually can be better for these metrics. Could you and you mentioned this already a little bit, could you maybe reiterate what makes a quantum machine learning or quantum computer different that could help in getting better expressibility and trainability and generalizability? And particularly, that you mentioned the Hilbert space, you mentioned entanglement. I think it would be good to touch on those concepts briefly and explain what they are and how they can help quantum machine learning.
Yeah, okay. I will do my best to try and keep it concise. Quantum computers, so their most basic element is a qubit, obviously named after the bit, just to stick quantum on the end. That's how we do most of the naming in quantum computing. And so a qubit is an interesting object because it exists. So whereas classical bits can take values 0 and 1, qubits, I like to think of them as existing on a sphere. We call the block sphere, where the poles are 0 and 1. And so what you get are points around the sphere for each bit. And so this means that when you combine them, the size of your space doubles for each qubit you add. So if I have 1 qubit, my space is 2-dimensional. If I have 2 qubits, then my space is 4-dimensional. And we get this exponential blow up of space for only kind of a linear amount of qubits. So that's my kind of expressibility. So you hope that with this kind of linear set, you can access a very, very large space of functions. And then we have entanglement. So this is another core property of quantum computing. And for us in machine learning, this tends to just mean correlation. So it's the ability to correlate between different qubits and different parameters. And so we hope at least that we're able to model more complex correlations than we would be able to with classical computers. It's also important to mention that entanglement is a property that you must have to be able to get any kind of quantum advantage. So if we're doing anything with a quantum computer and we're not actually making use of entanglement, then we could do it on a classical computer. And actually, you could probably do it faster on a classical computer.
So basically, a computer with 0 entanglement it returns to being a classical computer, right? Without entanglement, it's not really quantum. So I think that's really important to have those two concepts: this exponential growth of a computational space, and on the other hand, this unique property of entanglement that is unique to quantum machine learning and that we can use in order to get some advantage. So that's we covered in this slide. So there is a couple of advantages. So faster training times, greater expressibility with fewer parameters, generalization using fewer data. Could you give some intuition about why quantum machine learning could do any of these things better?
I will do my best again. So this is fairly so the points that we've raised here are to do with some specific papers actually that have been published quite recently. The faster training times is actually quite an empirical thing. We often see this convergence quicker. And I'm afraid I couldn't give you intuition as to why necessarily that's true. If Julian has got anything there.
So faster training times on expressibility?
For the speed of training, yeah.
It's a very complicated topic, and sure, if you cover the other one, I will think about it in the meantime.
Okay. Okay, so greater expressibility with fewer parameters. That's just because, as I said, we have this kind of linear number of qubits, but we're in an exponentially large space. So the way that we're able to manipulate these individual qubits allows us to access this massive space. So we get this greater expressibility with the fewer parameters. And this fewer parameters also then leads into the trainability because we have less parameters to optimize. So we're hopeful that you can get away with using less parameters than you can for the large kind of classical machine learning models that we have currently, which use, in the orders of hundreds of thousands of parameters in some cases. For natural language processing models, it's something obscene, in the billions at least. And then finally, this generalization using fewer training data. So this is essentially saying that in certain cases, I don't actually need that many pieces of training data to be able to generalize to my test set. And this is important for certain problems in industry where it's quite difficult for you to get pieces of training data. It's quite costly. So for example, just over a year ago, we were taking part in the BMW Quantum Challenge. And this was looking at automatic assessment of machine parts, so looking for cracks in different machine parts. And these errors, these cracks happen at a very, very low rate. And it's very, very difficult to find these and quite costly to get hold of this data. So for certain problems like this is very exciting for us, as we get to use small amounts of data and hopefully generalize to this larger space.
But I was thinking in the meantime to try to come up with a good intuition for faster training times. And what I came up with, so I hope that you will agree, and then it triggers some thinking in the audience as well. And it's all about optimizing the optimization landscape of your loss function, right? And the more smooth that is, the better it would be to train. And the more flat it is, you get into all kinds of problems. We'll touch a bit on that later. And I think that the key element why there may be faster training on quantum machine learning models is because you have this better representation of your model in a larger computational space. And it sort of gets easier to find the right gradient descent towards a local minima, because you have a more better represents the problem in this optimization landscape. Would you agree with my improvised intuition?
I think that seems reasonable. Yeah.
I guess something we can improve with the audience as well. So I think that's what we see really clearly here is that there are some elements from quantum machine learning, like the exponentially large space that will have some impact on the expressibility, like the entanglement as a property that helps in training and generalizability. So really unique properties from quantum technology and quantum computing that will help in some quantum machine learning problems to work better. But it's important to remember that this is still a theoretical exercise to a large extent, and that until we have done this on a large scale, it remains to be seen if this will eventually work out. But especially, I think it's quite promising that in the last 2-3 years, something like that, there have been loads of papers that have explored this theoretical improvement, and there is really significant hope that this eventually will become better. So maybe to dive into what these quantum machine learning models are. Remember that we picked this top right corner where we have a quantum algorithm working on classical data, right? So it's this one particular quadrant of this table. And you already mentioned that that these type of algorithms are mostly described as variationally optimized quantum circuits. What do we mean by that?
Yeah, so what we tend to mean by this, in at least its most basic form, is that I've taken some classical data and I've embedded it into my quantum computer somehow. You can see there on the left, that's the first part of the thing that I'm doing. And then I'm pushing it through a trainable quantum circuit. So this is just, in essence, a matrix which is parameterized by, a various number of parameters, and then we're pushing it through to this final measurement stage. So you can view this, and many people do, as a quantum neural network. So it's just some layer that you can slot into your classical neural network. So this can take many forms. Again, I've been quite general here, but there are things you can do, like, for instance, on the right-hand side, we have this measurement of the quantum state. So we're projecting it out into a series of zeros and ones. And actually, you can reduce the number of measurements that you take here, for example, and there are good reasons why you might want to do so. I've also suggested that the data embedding and the trainable quantum circuit there are separate. There are cases where you might not want to do this and you might want to mix them in. That's quite interesting and exciting. And in general, the best, quote unquote, best forms for these embeddings and circuits is not known. But there are a lot of experimentation at least going on at the moment to try and work out what some of these circuits might have to look like and what you might want to be able to do with the data embeddings.
So let me translate that maybe in some other words. So because I'm not sure if those terms are directly known. So data embedding, another way of saying that's basically loading classical data in your quantum circuit, right? And then we have a second, so the trainable quantum circuits, which maybe in other words could be an equivalence to the model that we have in a classical machine learning model, where we have weights and we have some parameters that we optimize. And then the unique quantum thing again that we have to measure it and return the quantum data again to classical data. My question is, what do you see as some of the challenges in these different steps? And maybe we can also use that as a means to answer one of the questions from the audience, which asks, can we use all classical AI models can we use quantum machine learning for all classical AI problems that we have today?
Okay, so to answer that first, there's a lot of work of what I like to call classical inspired algorithms, which are, we take a classical algorithm and we shove it onto a quantum computer. And there are some instances where you might get some sort of speed up from that, but in general, it's not necessarily clear at the moment whether you get speed up for all of these cases. And I think this is going to be another one of the cases where we're just going to have to push through some problems and see what sticks and see what goes well. I think adoption of these quantum techniques is going to be only via proof points in a lot of instances. Sorry, I lost what was the first part of the question?
So my first part, so I was thinking about, the problem with loading this data is that this can be such a expensive step. If we have big data streams, and typical, of course, the classical machine learning problems have large data sets, for example, NLP. And this is one of the steps that we have to take in our quantum machine learning models. Which can be one of the problems, right? How do we do that? How do we load that data? What is this something we can do for every data set?
Yeah, so the loading data problem is a big problem in quantum computing in general. So one of the interesting things about quantum computing is called the no cloning problem. So in classical computing, once you've loaded your data, that's it. I can copy it a bunch of times and put it elsewhere. But in general, with quantum computers, I can't do the same thing. So when I load some data onto my quantum computer, push it through some circuit and then measure it, I have destroyed some of the information. And I think that the way that I like to think about that is, here in example, I've got 4 qubits, but the space that I'm living in, at least my quantum state lives in, is 2 to the 4. It's 16 dimensional, but all the information I'm getting out are 4 numbers. So clearly I've lost some of the information along the way. So you want to be kind of as expressive as possible with your data embedding to make the most out of your data whilst it's on the computer, because you're going to have to load this data on and run it through a lot of times, especially for machine learning problems. So there are a various different number of ways you can do things. So earlier I described a qubit as living on the surface of a sphere. So one thing you can do is take your data point and use it as a rotation. So you can simply just rotate to another point on the sphere. That's one example of an embedding. You can do other things so because the space that you live in is higher dimensional, you can actually, instead of just loading, a piece of 4-dimensional data on here, I could load a piece of 16-dimensional, as long as I know the right way to do things. However, as always, there's a trade-off that comes with this. So in this case, it's the depth of the circuit will have to increase if I want to embed more complex data. whereas doing just this simple rotation, for example, only requires a low depth. And by that, I mean just the number of gates that you have to use to embed the data is quite low.
Perfect. So what we have is that there is some theory about how these models will work, but there are so many options, right? We can load this data, as you mentioned, through an angle, or we can load it with some other way. So there's various different approaches of loading this data, and they all have a little bit of different effect. And actually, we don't really know what's going to work best until we try that out. But it definitely is a challenge. So also to answer part of the question, can we load every classical machine learning model on this system? Well, maybe we could, but it probably doesn't make sense for most applications, because it's just root rule, and every speed up will probably much slower. So that's really about this loading first step, right? So many different approaches, all with their pros and cons. What can we say about this layer in the middle here? What is this? How does this relate to a classical machine learning model? Is there different layers? How do you do this?
Yeah, so this part here is kind of like our all-to-all like connectivity layers. So our actual hidden nodes in some neural network. And in this case, we break this down into individual gates once again, which we can parameterize. So the example we use often is rotation again. So we use certain rotations, but we can also do correlation through kind of controlled gates. So using the information from one of the other qubits to influence the rest of it. And this here again, it's not very well known what kind of the best structure for a quantum circuit is. In many instances, this will be application specific. And so a lot of your work will be trying to figure out for your given application, is this my best gate set? And one of the things that we like to do, at least in a lot of the circuits, kind of naively, is we like to put a lot of symmetry in, because humans like symmetry. So you'll often see structures that look, quite pretty in some instances, and it turns out that these symmetries actually are quite a good thing, and can help us. But again, a lot more work needs to go into try and figure out why exactly these structures are good.
Perfect. So let's move on to the one of the challenges of quantum machine learning, called barren plateaus. I think some of the people might already know them by a different name. I think barren plateaus is more used in the quantum machine learning world, whereas vanishing gradients might have been more known. Why is this such a problem for quantum machine learning? And what is it to start with?
So barren plateaus, as you said, are closely related to the vanishing gradient problem. So it happens when the gradients that we use to update our machine learning models become exponentially small. And this is a problem in both classical and quantum models. The main difference here is that the way that we measure our quantum gradients is by estimating them from sampling. And when you have something that's exponentially small, to be able to estimate it to that kind of accuracy, you need an exponential number of measurements. And it's this exponential number of measurements that you take that is just going to vastly increase the training time. So for classical computers, you can just increase the number of decimal places that you take your gradient approximation to. So you don't get this exponential scaling. And that's the real problem with with barren plateaus in quantum computers. And we kind of see this a lot more with quantum computers because we have these exponentially large spaces. So we have a lot of problems navigating through such high dimensional spaces because they are very vast. So if I pick two random points in these spaces, the probability that they're close together is not very high. And that's where these barren plateaus coming from is just trying to work out how we kind of get these clusters of points closer together.
Right. So it's on the one hand, it's a virtue of these quantum machine learning models that they have this extremely large computational space. But if we don't manage that well, if we don't use that well, maybe occupy that space in a proper way, then we get it so spread out that this would just be too flat, so that we won't be able to calculate these gradients. Maybe let's have a question from the audience. Deepesh asked that already there's a lot of difficulties with explainability and the traceability of classical machine learning models. If we go back, maybe you can go back to the previous slide here. How does that, is that even more difficult for quantum machine learning? And will there be maybe even inherent problems with quantum machine learning about the quantum structure of a machine learning model?
Yeah, I think so. There's the initial barrier with quantum computing in general, that there is a level of knowledge that you need to be able to understand to talk about quantum machine learning. And part of that is down to the word quantum itself, which is not always a helpful word to tack onto things. But I think some of the correlations that you can talk about with entanglement are useful. But I think we still have this level of explainability that you're just not going to be able to get. I can't say why my parameters are going to a certain way. There are some models that suggest, so for natural language processing, they've built them in a certain way to define certain interactions that give you some idea of explainability, but on a very basic level, you still have the same explainability problem as classical machine learning.
So that won't be solved, and maybe even be harder just because people won't be able to understand it, because it's more and more difficult. Is it a problem additionally that because we have this measurements, right, we lose some of the information from these quantum systems, and quantum systems are always a stochastic or always a inherently stochastic process, that we have additional uncertainty about our models?
Yeah, I think this is another very good point. In that the answer that I get out is probabilistic in nature in a way that it's not in classical machine learning models. When we do these models, what we're actually doing is doing the same calculation, 1,000, 2,000 times, whereas on a classical computer we'd push it through only once, because these measurements, we have to estimate what these values actually are, and that doesn't help with explainability either, because we've got even more randomness in the model.
Yeah. How about, and this is also a question from Deepesh, how about the importance of data quality for quantum machine learning? So it's obviously this is already a big problem for classical machine learning. How do you think that will translate it to quantum machine learning?
I think it's going to translate similarly. You're still going to want very high quality data, and you might not need as much of it as we've already suggested, but it's the same for any machine learning model. You want as much training data and as good quality as you can get for it.
Yeah, I always also think about this as a the triangle of data quality, where on the lower level we have like the basis layer, the bronze layer or something, where it's all unstructured data. Then we structure the data, then we get features out of it, then we do some machine learning. And I think quantum machine learning will really live on the very top level of this pyramid. So we won't be able to do the large number of data crunching operations or something like that. Will only be on the very, very top level, because it's one of the tricky things to load this data into those models. And so probably will be more on heavily fine-tuned data and to the very specific predictions than to crunch large systems of data. So even I think it would be even more important than for classical machine learning to have proper data.
Yeah, for classical data with quantum algorithms, you're always going to be cleaning it first with the classical computer. You can't put noisy data onto this computer the same way that you can with a classical computer.
Yeah. And do you think that it could even work together? Would you see that that in one application there would be quantum machine learning, classical machine learning, and maybe a quantum processor, a GPU, and a CPU working together?
Yeah, so one of the things that we talk a lot about is this kind of heterogeneous compute environment. So where you have all these different parts. We know that GPUs, for example, work well for training these large deep neural nets. But there are also processes which CPUs are better for. And so we have this idea of a quantum processing unit, a quantum computer of some form. And I think it's likely in the future, we don't have a fantastic understanding necessarily of stuff that is the best optimization for putting stuff on CPUs and GPUs, but we will have to include QPUs in this environment. And I think a lot of this is working out, which processes work best where. And I do see that it will be, all three of those together, not just here's my quantum computer, that's it.
Perfect. So we have one other model that we want to share, which I think is an interesting one about quantum computer vision. What is the QCNN?
Yeah, so the quantum convolutional neural network is just kind of it's a certain quantum neural network model. So as I alluded to earlier, we can measure all of the outputs of some quantum circuit, or we can only measure part of them and throw those measurements away to some extent. And the quantum CNN does that exactly, except we do that these measurements part way through is the idea. And this problem of barren plateaus that we talked about doesn't actually appear in these quantum convolutional neural networks. So these models are really interesting to kind of explore and see what we can manage with them.
Cool. So, and these QCNNs also have shown no sign of this barren plateaus, of not having vanishing gradients.
Yeah. So my best guess on, so the proof for this is very, very involved. And my best guess on this is that this when you do these measurements, you're projecting your quantum state into a lower dimensional space. And it's being able to then navigate through this lower dimensional space. That means that you don't necessarily meet these barren plateau issues.
Perfect. So what I wanted to do from here on, we have quite some time left, and I have a bunch of things that I wanted to discuss with Joe, but I also wanted to just make it as open as possible. Just whatever question you have around quantum machine learning that you want to ask to either of us, either about what are some of the theory or what are some of the progress and scientific developments, or what are some of the best practices, some of our experience there. So maybe let me start with one question, then I can read the others from the chat. What do you think is quantum machine learning really going to be used for? Where is this going to make the biggest impact?
Oh. That is a very difficult question, and if I could answer that definitively, I'm sure I could make a lot of money. So I think the really big application, which won't be for quite a few years, will be this quantum to quantum. So optimizing quantum sensors using quantum machine learning processes, I think is where it's really at. If you look at some of the talk in the community at the moment, Zapata are very big on generative, is it generative quantum machine learning? So being able to make these distributions, these really interesting distributions from it.
Cool. I also think that one way to look at it is to see quantum computers can only be better at something where classical computers is not that good, right? Because if quantum machine learning or quantum computing in general, or sorry, if classical computing is already super good, it will be very difficult to beat. So I think generally classical machine learning is already extremely good in things like natural language processing for most language applications, for most computer vision type of applications. I think also that usually if there's a lot of data, classical machine learning might work pretty well if there's really abundance of data. And if classical machine learning won't work well in those cases, it's undoubtful if quantum machine learning will be better there anyway, because all the data processing is not really a thing. So I would say in general, large number of data sets is just better for classical machine learning than for quantum machine learning. So I think that can be really another approach to see where do we find applications today where classical machine learning really falls short, where we really can't do what we want to do? And my feeling would be that it will be in applications, well, first of all, that have very little data. And then second, of things that we can't intuitively well explain, where we don't have good heuristical solvers for something. Maybe things like quantum chemistry, or maybe sequencing of DNA or something like that. Not sure if that. Do you agree with that?
Yeah, I think certainly this idea of the low data environments is very exciting for quantum computing.
So I'll also be curious to hear if someone from the audience has any ideas about that. Where do we see these low data volume applications where we would really want to do something better, but it just doesn't work right now? Let me first ask a question from Dipesh. Are the measurement so the measurement of outcome from quantum model follow the same metrics already defined in the classic? So I'm not exactly sure what is meant by that. The measurement of outcome. So do you mean by
so maybe I can ask that question if that's fine.
Yeah, absolutely.
Yeah, so in classical machine learning models, there are already the matrices which are already defined. How do you find success of a particular model? Whether it is whether the predicted results are good quality or not, right? So there are KPIs and matrices already defined. How do you confirm whether the outcome is good or not? So in the quantum way of working, will all those measurements changes or they remain the same?
So things like recall, precision, if they are the same or not. I assume. So let me give my perspective. I think that in the end, quantum machine learning is a tool, and we just have to see if end-to-end application if it works well. And I guess in an eventual application, there will be a combination of classical and quantum machine learning all working together, and we just have to see if it solves whatever business problem we are solving. And the metrics don't change. It's just about the precision or the accuracy or whatever we're trying to measure will remain the same. Now, because that is really difficult to judge at this point in time, we need to do with something else. So we need to identify that the potential of these models in some other way. And for that, there is some theory around those concepts that we described before. So the expressibility of a model, the generalization, the trainability. And I think there are some unique properties or maybe theories or something that are introduced in the quantum technology world. So for example, there's things like effective dimension, which is, well, actually not exclusive to quantum machine learning, but I guess is now discussed again. So maybe Joseph, can you explain what this particular metric is about and why it helps in judging the quality of a quantum machine learning model?
Yeah, so I think in general that expressibility measures are quite difficult to compute. So if we see things like so classical machine learning, we see things like VC dimension and Rademacher complexity, and these are not only kind of complex to compute, but also the bounds that they're used in are often quite slack. So they're kind of difficult to judge how effective they are. So the effective dimension is a quantity that tries to express, at least in my interpretation, the number of parameters or how efficiently you're using your parameters in your machine learning model. So, for example, a way of expressing how complex a model can be is by saying I've got 5 million parameters, but if I'm not using those parameters very well, then my model is far too complex, and realistically I want to be focusing on a low number of parameters, and so any optimization steps, I'm effectively wasting time looking at all of these different parameters. So if I have a model that has a high effective dimension, so where I'm using a large number of these parameters well, then this quantity can tell me that maybe this is the kind of model, kind of architecture that I want to be implementing. And so this is kind of independent of classical and quantum. This is done by just I put some model into this and I spit a number out. And we've done this for some quantum models on a very, very small scale for, again, the BMW Quantum Computing Challenge. And you can start to see some evidence at the small scale that quantum variational quantum circuits kind of that nature do actually have this higher effective dimension.
So I hope that this touches your question as well. So there's both metrics from the classical world as from the quantum world, which can be helpful. And I guess it's always a bit of a trial to find out what works eventually. And that is exactly the point that we're trying to make. It's really just as much a science as an art to find the right model and to make sure that it works better. And I think that is really an opportunity for us as well, because it won't be that there will be one time an invention that there will be a better model and then everyone just uses it. It will be something that we'll have to highly adjust it to the data set that we have, to the end goal that we have, to the other data or algorithms that we have, and making it work together with them. And for all of them, there are some metrics that we may be able to use, but that we have to figure out in a case per case, actually. So another question: what are the different channels available to learn and hands-on quantum machine learning? What have you personally used, Joe? What is there? For example, I know PennyLane and IBM Qiskit, and there's a bunch of resources. Would you have a specific recommendation?
Yeah, so practically a lot of the work that I've done has been trying to use PennyLane, which has quite a good toolkit for quantum machine learning in general, and they've also got some researchers there that I really rate some of the papers coming out. I know also that IBM Qiskit has a very, very detailed workbook that is definitely worth having a look through, which also has a lot of the code examples as well. And IBM has the advantage that you can access the computers very easily, which I think is very important for doing kind of experiments with quantum ML. So
we can put those links in the chat. So both PennyLane, it's from a company called Xanadu. They have produced a bunch of tutorials and a whole learning environment online, as well as the Qiskit textbook from IBM. We put them on the chat, so I think they are great learning resources. One dream that I would have that maybe we could do someday as Capgemini is to release the next MNIST data set for quantum machine learning, right? Because what we talked about until now was that it's really difficult to assess whether quantum machine learning is going to be better, because we can't run it in large scale, and we also can't really prove it, but that would be really restricting, only to go on what we can prove. So we want to eventually try it out in small cases and then have a data set where we can compare different models. And I think in the classical world we've had MNIST for number classification, which was really one of those things that was instrumental in pivoting people against each other and trying to improve on the different models and really sort of initiating a race towards the best model. So is there any quantum equivalence of this model, and what should be some of the characteristics of this data set?
Yeah, so I think this is again another very interesting problem for quantum machine learning, is that we can, for example, just use all of the same data sets that we already have for classical machine learning. If you can find ways to embed and utilize quantum algorithms, then you can do the same comparisons. But also we can generate data sets that are quantum states. So if I give you the instructions of how to build a certain data set, then we can use these to benchmark on. Unfortunately, these are kind of plagued by errors of like preparing the states, for example. That's a non-trivial problem. And if it's complex to prepare the states, then you might not be able to do much with the states once you've produced them, because the quality of the computer that you're running on might not be good enough to do much more. So it might be something that we have to gradually build up as our computers get bigger. I think there's also potential for more quantum states. So through certain experiments, if we're able to get ways of passing quantum states that we generate through some process into a quantum computer, then it may be possible in the future to use these kind of states to do quantum ML on. And I think those would be very interesting data sets.
So maybe another question for me. What do you think is some of the key research areas that the quantum machine learning community is moving towards? What will be, what will be the big topics in the next few years?
So I think at least for me, it's looking at larger problems. I think we've kind of got an appetite for these bigger data sets now. Given the size of our computers actually allows us to load slightly larger things on. I think there's certainly some interesting thoughts about how to parallelize computations and look at trade-offs for the depth of the computation that you're able to do versus kind of the width, so the number of qubits that you actually use. I think that's very interesting. And then for me personally, kind of the methodology that you use to design these quantum neural networks, the variational quantum circuits that we've been discussing, if there are ways or processes that you can use to tailor them to your problem, I think that's an area that we're getting closer and closer to being able to talk about.
Excellent. So I want to give the audience a final opportunity to ask a question. And if not, I would like to thank you, Joe. I realize that I put you on the spot with some questions that, not just you, but no one in the whole industry doesn't know yet, because it's just, an active research area. So it's not a, it's a very fascinating topic that's continuously being developed still. So there's a lot of unknowns and therefore, I think a lot of opportunities as well, because I think there are so many areas of classical machine learning that can have some spillover effect into quantum machine learning, right? There's so much to be discussed, to be discovered. Can we do? Recently there was this work from the stable diffusion models. Can we make a quantum version of that? I don't think anyone has looked into that yet. Say never, never. It's a big world, but at least there are so many interesting opportunities to work on. And I think that's also something that that is interesting for us at Capgemini, because we have a lot of this classical machine learning knowledge. So I would invite everyone to start thinking about this and to maybe check up with Pendelane or with IBM Qiskit textbook, because they're excellent resources. And if there are no further questions, I would like to thank everyone for being here, and I think we can close off. Is there anything, Ishmeet, that you would like to close off with? Maybe promotion for the next event or something?
So we don't have any event planned as of now, but I will be sending out an email. But thank you, Joseph and Julian, for this wonderful session. Thank you, everyone else, for joining us today. Have a great day.
Thank you.
Thank you very much.